start of the 20th century, many physicists might have thought they'd soon be out of a job. It was believed that the laws of physics were complete. At the 1900 British Association for the Advancement of Science, the engineer and physicist Lord Kelvin said, "There is nothing new to be discovered in physics now. All that remains is more and more precise measurement." But nothing could be further from the truth. The 20th century saw two major upheavals in our entire perception of the universe. The first, when Albert Einstein formulated his special and general theories of relativity. And the second, the multitudinous developments in the wild world of quantum mechanics. We can understand the essence of these two theories in terms of how they relate to the four fundamental forces underpinning the universe. Einstein's general theory of relativity deals with the force of gravity, a force very familiar to us in our daily lives. It's not just the force that keeps our feet on the ground, it's also keeping the planets in motion around the sun. And it's responsible for the tides. Further afield, it also creates black holes, thought to lie at the center of every galaxy. Without gravity, the material present before the birth of the solar system would never have clumped together to form the sun. It would never have formed the Earth, and never have formed us. Einstein's theory describes this force not as a mysterious action at a distance, but as the dynamism of space-time itself, the consequence of masses, like the Earth, bending the space-time around them. Most of everything you see around us is made of atoms, but atoms are mostly nothing, which is why this diagram is not to scale. In fact, if an atom were the size of a skyscraper, the nucleus would have to be as thick as a sheet of paper. The nuclei of atoms contain protons and neutrons, both of which are composed of particles called quarks, or quarks. These particles are held together by the aptly named gluons. Gluons are exceptionally strong, and that's why they carry what is called the strong nuclear force. It has long been known that electricity and magnetism are two faces of the same coin, called electromagnetism. This is also a familiar force, and it is carried by particles called photons. Finally, there is the weak nuclear force, responsible for a particular type of radioactive decay, in which a neutron decays into a proton, an electron, and an electron antineutrino, via a mediating particle of the weak nuclear force. These three forces are described by quantum theory, called the Standard Model of Particle Physics. The Standard Model describes the fundamental forces as particles called bosons, and it describes everything else as particles too, hundreds of them. However, some people regard quantum theory as more maths than physics. The properties of all these particles sometimes seem arbitrary, but they can be defined with startling precision with the equations. But quantum mechanics does not answer the more profound questions, such as, what is a particle? In contrast, Einstein's theories are elegant and have physical as well as mathematical descriptions for describing the universe on a very large scale. But both relativity and quantum mechanics are proven physics, and when you try to use both of them together, neither of them work. And what physicists really want is a unified theory of everything. The Standard Model already unifies three of the fundamental forces. In fact, all it takes to do that is temperature. But is it possible to go further and add gravity to the mix? M-theory is at the cutting edge of scientific research. Many feel that it is the only hope for explaining the origin of the universe itself. M-theory redefines particles as the vibrations of membranes that have up to 11 dimensions. But there are problems with it. There's absolutely nothing of what scientific theories need most: experimental evidence. What's more, they don't know what the M should mean. Physics is far from complete.